You asked me if an ordinary person, by studying hard, would get to be able to imagine these things like I imagine them. Of course, I was an ordinary person who studied hard. There's no miracle people. It just happens they got interested in this thing, and they learned all this stuff. They're just people. There's no talent, a special miracle ability to understand quantum mechanics, or a miracle ability to imagine electromagnetic field that comes without practice and reading and learning and study. So if you say, take an ordinary person who's willing to devote a great deal of time and study and work and thinking and mathematics and finance, he's become a scientist.
I'm sitting next to a swimming pool and somebody dives in and she's not too pretty, so I can think of something else. I think of the waves and things that have formed in the water. And when there's lots of people have dived in the pool, there's a very great choppiness of all these waves all over the water. And to think that it's possible, maybe, that in those waves is a clue as to what's happening in the pool. That some sort of insect or something with sufficient cleverness could sit in the corner of the pool and just be disturbed by the waves, and by the nature of the irregularities and bumping of the waves, have figured out who jumped in, where and when, and what's happening all over the pool. And that's what we're doing when we're looking at something. The light that comes out is waves, just like in the swimming pool, except in 3 dimensions instead of the 2 dimensions of the pool as they're going in all directions. And we have a 1/8 of an inch black hole into which these things go, which is particularly sensitive to the parts of the waves that are coming in a particular direction. It's not particularly sensitive when they're coming in at the wrong angle, which you say is from the corner of our eye. And if we want to get more information in the corner of our eye, we swivel this ball about so that the hole will move from place to place. Then it's quite wonderful that we can figure out so easy. That's really because the light waves are easier than the waves in the water are a little bit more complicated. It would have been harder for the bug than for us, but it's the same idea, to figure out what the thing is that we're looking at a distance. And it's kind of incredible, because when I'm looking at you, someone standing to my left can see somebody who's standing at my right. That is, the light could be going right across this way, the waves are going this way, the waves are going this way, the waves are going this way. It's just a complete network. Now, it's easy to think of them as arrows passing each other, but that's not the way it is, because all it is something shaking. It's called the electric field, but we don't have to bother with what it is. It's just like the water height is going up and down. So there's some quantities shaking about here, and in a combination of motions that's so elaborate and complicated that that result is to produce an influence which makes me see you at the same time completely undisturbed by the fact that there are influences that represent the other guy seeing him on this side. So that there's this tremendous mess of waves all over in space, which is the light bouncing around the room and going from one thing to the other. Because, of course, most of the room doesn't have 1/8 inch black holes. It's not interested in that light, but the light's there anyway. I mean, it bounces off this and it bounces off that, and all this is going on, and yet we can sort it out with this instrument. But beside all that, those waves that I was talking about in the water, maybe they're so big, some of them, and then you can have slower swashes, which are longer and shorter. And perhaps our animal who's making his study is only using waves between this length and that length. So it turns out that the eye is only using waves between this length and that length, except those two lengths are 100 thousandths of an inch. 100 thousandths of an inch. And what about the slower swashes, the waves that go more slowly, that have a longer distance from crest to trough? Those represent heat. We feel those, but our eye doesn't see them focused very well. We don't, in fact, at all. The shorter waves are blue, the lighter, and the longer waves are red. But when it gets longer than that, we call it infrared. All this is in there at the same time. That's the heat. And then these waves get longer and longer, and all through the same space. All these things are going on at the same time, so that in this space there's not only my vision of you, but information from Moscow radio that's being broadcast at the present moment, and the seeing of somebody from Peru. So this big field, this area of irregular motions of this electric field, this vibration, contains this tremendous information. And it's all really there. That's what gets you. If you don't believe it, then you pick a piece of wire and connect it to a box. And in the wire, the electrons will be pushed back and forth by this electric field, swashing just at the right speed for a certain kind of long waves. And you turn some knobs on the box to get the sloshing just right, and you hear Radio Moscow. Though you know that it was there. How else did it get there? It was there all the time. It's only when you turn on the radio that you notice it. But that all these things are going through the room at the same time, which everybody knows but you got to stop and think about it to really get the pleasure about the complexity, the inconceivable nature of nature.
The mathematicians only are dealing with the structure of the reasoning, and they do not really care about what they're talking. They don't even need to know what they're talking about, or as they themselves say, or whether what they say is true. Now, I explain that. If you state the axioms, you say, such and such is so, and such and such is so, and such is so, what then? Then the logic can be carried out without knowing what the such and such words mean. In other words, mathematicians prepare abstract reasoning that's ready to be used if you will only have a set of axioms about the real world. But the physicist has meaning to all the phrases. And there's a very important thing that a lot of people who study physics that come from mathematics don't appreciate. The physics is not mathematics, and mathematics is not physics. One helps the other. But you have to have some understanding of the connection of the words with the real world. And this is a problem which is not a problem of mathematics at all. Mathematicians also like to make their reasoning as general as possible. If you say, I have a three-dimensional space, ordinary space, I want to talk about ordinary space. You're in it, and you measure distances, and there are three numbers you need to tell where something is. You go breadth, width, and height, three-dimensional space, and you begin to ask them about theorems. Then they say, now look, if you had a space of n dimensions, then here are the theorems. Well, I say, yeah, but I only want the case 3. Well, substitute n equals 3. And then it turns out that very many of the complicated theorems they have are much simpler because it happens to be a special case. Now, the physicist is always interested in a special case. He's never interested in the general case. He's talking about something. When you know what it is you're talking about, that these things are forces, and these are masses, and this is inertia, and this is so on, then you can use an awful lot of common sense, seat-of-the-pants feeling about the world. You've seen various things. You know more or less how the phenomenon is going to behave. Well, the poor mathematician, he translates it into equations, and the symbols don't mean anything to him, and he has no guide but precise mathematical rigor and care in the argument. The mathematical rigor of great precision is not very useful in the physics, nor is the modern attitude in mathematics to look at axioms. Now, mathematicians can do what they want to do. One should not criticize them because they are not slaves to physics. It is not necessary that just because this will be useful to you, they have to do it that way. They can do what they will. It's their own job. And if you want something else, then you work it out. There was a time when the newspapers said that only 12 men understood the theory of relativity. I don't believe there ever was such a time. There might have been a time when only one man did, because he's the only guy who caught on before he wrote his paper. But after people read the paper, a lot of people kind of understood the theory of relativity in some way or other. But more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics.
We have a theory which is called quantum electrodynamics, which is our pride and joy. It's so successful and it's so wide in its application. And what I would like to tell you about is that theory, how it works, or how it looks like it works, what the world looks like from that point of view. The physics has got a history, at least its theoretical history, of synthesis perpetually. Of course, the experiment is always finding new phenomena. The problem is to work them together, and sometimes we see that they're different aspects of the same phenomenon. An example is, of course, the simplest and earliest one is that the laws of motion became, in the theory, explained the properties of heat, because heat was motion, and if you knew how motion worked, you could understand the thermal properties. It also explained the properties of sound, which is otherwise a mystery, as the motion of the atoms and waves in the gas. Aside from that, knowing the laws of motion, you had to know Newton, who gave us the laws, worked out the laws of motion, also gave us another theory about the forces between large masses and distances from one another called the theory of gravity. Well, that's just that thing, the theory of gravity, is well known and understood pretty well, but is not what I'm going to talk about. As the time went on, phenomena associated with electricity, rubbing combs in your hair and things like that, and magnetism became interesting to the experimental physicists, and they discovered relations between them experimentally until they saw, ultimately, there were not two different phenomena, but different aspects of the same thing. Another phenomenon that Newton had studied was light. So without time, it looked at first like there were many things: motion and gravity, electricity and magnetism later, and light. But when Maxwell put together the laws of electricity and magnetism, he found out that the behavior, the equations that he had produced expectation that would be behavior of waves that would propagate at a speed, which was figured out from electrical measurements, but came out the same as the speed that light actually propagated. And so there was a new theory of light, which is that it was an electromagnetic wave, and Maxwell's great synthesis in 1873 was to connect electricity, magnetism, and light. Light is just one aspect of the electromagnetic wave, which can have different kinds of wavelengths from that point of view. And if you have different wavelengths, if the wavelength is very short, between about 400 millionths of a meter, no, of a centimeter, 400 millionths of a centimeter and 700 millionths of a centimeter, then you see it directly with the eye. But if it gets longer, the wave is, well, it's a long end, it's red, and then the other end, it's blue. And if it gets longer than the red, we call it infrared. The rays are there, but the eye doesn't see them. The pit viper has an eye that sees the infrared. And if you go in the other direction, to beyond the violet, then we can't see it again, but the bee has an eye that sees the ultraviolet. And if we go still further to the far ultraviolet, no animal has it that can see it, but we can make instruments that detect it, or photographic plates, and so on, up into X-rays and so forth. And down in the other direction, far infrared, you get into radio waves, and we can build instruments that detect them, and we can use them to advertise soap. In addition, so that is an enormous range of one property, the wavelength. A range of phenomena that's a complete, enormous spectrum. The spectrum we see with the eye is a very narrow range, and it's the entire spectrum. It's all put together with the one theory of electromagnetic waves. I'm going to talk about that part of it. I'm going to call it light, instead of saying electromagnetic radiation. Light is what we see, is only one little part, but from the physicist's point of view, the accident that the human eye happens to be sensitive to waves from here to here is not essential. The phenomena are the same over the whole range, and I'm going to call them all light, but it could be radio waves or X-rays or what have you. Next thing that was discovered was the structure of the atoms, and that, I'd like to remind you that you have, I believe, a Nobel Prize winner from New Zealand before, Mr. Rutherford, who was, I believe, a New Zealander, who worked out that the atoms had nuclei. You know, it seemed always here, I've only been here a few days, everybody's talking themselves down. I thought this would be a happy country, but something's happened to you. You've got plenty of room and not too many people, and it looks like it ought to be good. Anyway, don't forget you had Rutherford, so it's okay. Anyhow, he had a theory of he developed our understanding of the atoms as having a tiny core, it's very heavy, with the particles going around it, electrons. Now, supposing that the electrons went around according to the laws of motion of Newton, some properties of matter could be understood, supposing the atoms were made that way. But most of the time it failed. And it became more and more of a crisis in physics to understand what matter was like, because it looked so obviously right that it had to be electrons going around nuclei, and yet nothing worked when you worked it out. And the discovery was made then in the discovery of quantum mechanics, first in the behavior of light and then in the behavior of matter, and finally culminating in 1926 with the full equations of quantum mechanics, which told us that the laws of motion of Newton were not right and had to be modified to other laws, which are quantum laws of motion. And when this quantum laws of motion were applied to electrons to explain the properties of matter, it was a fantastic success. The properties of the atoms could be all worked out mathematically, in principle at least, and the simple atoms in detail. And therefore, the theory behind chemistry, which atoms combine with which, at what rate, and so forth, is in principle. Theoretical chemistry deeply is physics. It's not a joke. The chemist will admit that's exactly his point of view, that the understanding of the atoms in the deepest level is physics, except that the atoms have so many particles in them, it's very hard to calculate what's going to happen, so he has to use a lot of empirical rules to help him. But as far as we can tell, there's nothing about chemistry that's not understood ultimately as the behavior of electrons following the laws of motion of quantum mechanics. This defines the properties of all substances also, and so that the whole theory of the properties of ordinary substances and the chemical properties and so forth have all been reduced to the motion of electrons. In the meantime, the theory of light and its interaction with matter, which was Maxwell's equations, had to be modified to become a quantum theory also. Oh, I forgot to mention that during this time, somewhat to one side of the way I want to go in these lectures, I'm not going to discuss much about relativity, but the theory of relativity was developed, and that just makes it easier for us to guess laws. It tells us if we know how something varies in space, then we know how it varies in time, or vice versa. That there's a nice relationship between the behavior in space and behavior in time, and that it's all sort of different aspects of the same geometrical thing called space-time. At any rate, Dirac, using the principles of relativity and the new quantum mechanics, found a wonderful theory, as simple as possible thing you could write down for the motion of electrons, Dirac's theory of electrons, and that was the situation about 1927 or 8. But the problem of the interaction of electrons with light, which was the complete quantum theory of electrodynamics, in other words, make Maxwell's equations of light, of electricity and magnetism, and the theory of motion of electrons, all into one grand theory, was accomplished in 1929 in the theory that was called quantum electrodynamics. Trouble with it was nobody could figure anything out, or better. When they did figure it out, they got nutty answers. If you didn't do it too carefully, you got a reasonably good answer for a problem. But if you carried it out very carefully, you would get some silly answer like zero or infinity or absolutely absurd results. This strikingly lasted for 20 years while people tried to figure out what the correct theory was. During this time, experimenters were measuring things more and more accurately. The theory of they found a few things with very subtle effects, saying that you don't understand it, meaning I don't believe it, it's too crazy, it's the kind of thing I'm not going to accept it. The other part, this kind, I hope you'll come along with me. You'll have to accept it. because it's the way nature works. If you want to know the way nature works, we looked at it carefully. Look at it, that's the way it looks. You don't like it? Go somewhere else, to another universe where the rules are simpler, philosophically more pleasing, more psychologically easy. I can't help it, okay? If I'm going to tell you honestly what the world looks like to human beings who have struggled as hard as they can to understand it, I can only tell you what it looks like, and I cannot make it any simpler. I'm not going to do this. I'm not going to simplify it. I'm not going to fake it. I'm not going to tell you it's something like a ball bearing on a spring. It isn't. So I'm going to tell you what it really is like, and if you don't like it, that's too bad, okay?
We're all connected to each other biologically, to the earth chemically, to the rest of the universe atomically.
I think nature's imagination is so much greater than man's. He's never gonna let us relax.
We live in an in-between universe where things change alright, but according to patterns, rules, or as we call them, laws of nature.
I'm this guy standing on a planet. Really, I'm just a speck. I'm just a speck compared with a star. The planet is just another speck. To think about all of this, to think about the vast emptiness of space. There's billions and billions of stars, billions and billions of specks.
The beauty of a living thing is not the atoms that go into it, but the way those atoms are put together. Cosmos is also within us. We're made of star stuff. We are a way of the cosmos to know itself.
Across the sea of space, the stars are others. We have traveled this way before, and there is much to be learned.
We're all connected to each other biologically, to the earth chemically, to the rest of the universe atomically.
I find it elevating and exhilarating to discover that we live in a universe which permits the evolution of molecular machines as intricate and subtle as we.
I know that the molecules in my body are traceable to phenomena in the cosmos. That makes me want to grab people in the street and say, have you heard this?
The beauty of a living thing is not the atoms that go into it, but the way those atoms are put together. The cosmos is also within us. We're made of star stuff. We are a way of the cosmos to know itself.
There's this tremendous mass of waves all over in space, which is the light bouncing around the room, going from one thing to the other, and it's all really there, really there. But you gotta stop and think about it, about the complexity to really get the pleasure. It's all really there, really there. The inconceivable nature.
Boy, it's impossible to have any information ahead of time as to which hole it's going to go through when the light is out or when the light is on or out in a circumstance where the experiment is set up there to produce this interference. So it is not a lack of unknown gears or lack of internal complications that makes nature have probability in it. It seems to be in some sense intrinsic. Someone has said it this way: nature herself doesn't know which way the electron is going to go. A philosopher once said, pompously, "It is necessary for the very existence of science that the same conditions always produce the same result." Well, they don't. You can set up the electrons in any way. I mean, you set up the circumstance here in the same conditions every time, and you cannot predict behind which hole you'll see the electron.
Again. But if you made it go fast enough, it'll fall into the hole. And so if you have something like wood in oxygen, there's carbon in the wood from a tree, and the oxygen comes and hits it, carbon, but not hard enough. It just goes away again. The air is always coming, nothing's happening. If you can get it faster, by heating it up somehow, somewhere, somehow, get it started, a few of them come fast. They go over the top, so to speak. They come close enough to the carbon and snap in. And that gives a lot of jiggly motion, which might hit some other atoms, making those go faster so they can climb up and bump against other carbon atoms, and they jiggle, and they make others jiggle, and you get a terrible catastrophe, which is one after the other. All these things are going faster and faster and snapping in, and the whole thing is changing. That catastrophe is a fire. It's just a way of looking at it, and these things are happening. They perpetual. Once it gets started, it keeps on going. The heat makes the other atoms capable of reaching to make more heat to make other atoms, and so on. So this terrible snapping is producing a lot of jiggling. And if I put, with all that activity of the atoms there, and I put a cup of coffee over that mess of wood that's doing this, it's going to get a lot of jiggling. So that's what the heat of the fire is. And then, of course, if you see, this is what happens when you start to think. You just go on and on. Wonder how did it get started? Why is it that the wood's been sitting around all this time with the oxygen all this time, and it didn't do this earlier or something? Where did I get this from? Well, it came from a tree. And the substance of a tree is carbon. And where did that come from? That comes from the air. It's carbon dioxide from the air. People look at trees and they think it comes out of the ground, that plants grow out of the ground. But if you ask where the substance comes from, you find out, where do they come from? The trees come out of the air? They surely come out of the air. No, they come out of the air. The carbon dioxide in the air goes into the tree, and it changes it, kicking out the oxygen and pushing the oxygen away from the carbon and leaving the carbon substance with water. Water comes out of the ground, you see. Only how did it get in there? It came out of the air, didn't it? It came down from the sky. So in fact, most of a tree, almost all of the tree is out of the ground. I'm sorry, it's out of the air. There's a little bit from the ground, some minerals and so forth. Now, of course, I told you the oxygen, we know the oxygen and carbon stick together very tight. How is it the tree is so smart as to manage to take the carbon dioxide, which is the carbon and oxygen nicely combined, and undo that so easy? Life. Life has some mysterious force. No, the sun is shining. And it's the sunlight that comes down and knocks this oxygen away from the carbon. So it takes sunlight to get the plant to work. And so the sun all the time is doing the work of separating the oxygen away from the carbon. The oxygen is some kind of terrible byproduct, which it spits back into the air, and leaving the carbon and water and stuff to make the substance of the tree. Then when we take the substance of the tree and stick it in the fireplace, and there's all the oxygen made by these trees, and all the carbon would much prefer to be close together again. And once you let the heat to get it started, it continues and makes an awful lot of activity while it's going back together again. And all this nice light and everything comes out, and everything is being undone. You're going back from carbon and oxygen back to carbon dioxide. And the light and heat that's coming out, that's the light and heat of the sun that went in. So it's sort of stored sun that's coming out when you burn a log. Next question, how is it the sun is so jiggly, so hot? I gotta stop somewhere. I'll leave you something to imagine.